coming today. It's my pleasure to introduce my graduate student, PhD student, Andrew Dzambo, who came to join us, I think, in 2015, if I'm correct? 16. January of 16, right. One of the rare winter students. So Andrew did a BS in meteorology at Penn State University. And he got that in 2013 and then went down to Oklahoma and worked with Dave Turner, who a lot of us know quite well because he was on the faculty here before going to Oklahoma. Like I said, he joined my group in 2015, already having published 2 papers out of his master's research. And he's been very productive actually since he's been here as well, having published 1 paper on the material you're going to see today, with 2 others in preparation, and then he's also managed to publish a paper that stemmed from a class project with Matt Hitchman. Yeah, clouds, I was reading the word clouds. And also a paper that I think is soon to be accepted, or is it already accepted in BAMS?
I just went back for revisions, right?
Okay, but about our, it's about our climate class that we teach in the summertime.
Yeah, AOS 102.
Yeah, so AOS 102. But besides all of that, Andrew's found a lot of time for other sort of leadership and social activities. He's been a great boost to my research group, organizing several outings. And you may also recognize Andrew as the person who started the AOS Pi Day, so I think this is a good time to kind of use this as an advertisement. Yeah. Are you still soliciting entries?
Well, Miguel's kind of taking that over now, but yeah, the more pies we can get, the better. I'm definitely going to bring one in.
Okay. Yeah. So I encourage everybody to participate in Pi Day. Also starting the AOS SSEC softball competition, and he's also been captain of the broomball team for 4 years in a row. I think that's a pretty impressive stat. Yeah. Also, I think this is fairly new since coming here, but you've become a pretty avid runner since you joined the research group. This is something that seems to happen to all of my students. I don't know when did you complete your first marathon? Actually,
back in November.
Back in November, he completed his first marathon, so that's a huge achievement as well. So anyway, without further ado, so obviously quite the track record here. But Andrew today is going to again talk about the research that he's been conducting from the Oracle's field campaign. I guess I will do one more quick anecdote that shortly after joining my research group, Andrew and I went down to Namibia as his sort of first foray here into running the cloud radar on an aircraft. And I feel, I don't think it's maybe too big a statement to make that was a fairly life-changing experience for you, Andrew. I remember you being in the field for the first time, like with really wide eyes, and then trying to, sort of learn that whole new aspect of our field. So hopefully Andrew will talk a little bit too about his experiences in the field as he's kind of conveying some of the work he's doing on this. Yeah. So go ahead, Andrew. I will say, doing field work definitely convinced me that this is definitely the right career path for me. Just being out and being able to see everything in situ, no pun intended. My presentation today, I guess, will be on a remote sensing perspective of cloud and precipitation processes observed from Southeast Atlantic Stratocumulus clouds, again, taken from the Oracle's experiment. So there's a lot of things, when we talk about Cloud-Aerosol-Precipitation Interactions, and, you could probably spend an hour talking about this. So I'm going to distill down to 4 main motivations, I guess, that I have for my dissertation here, and, expand upon them individually here. So first off, we know that stratocumulus clouds are the dominant type in the Earth's subtropical oceanic basin. So if you look in the Southeast Atlantic, Southeast Pacific, Northeast Pacific, that's pretty much the main cloud type that you see there. In these basins, they're especially prone to, aerosol interactions. And when we think about cloud aerosol and precipitation interactions, they're, from a climate modeling perspective, they're among the most widely uncertain processes in today's climate models. And as an extension of that, they're also one of the most important drivers of the global energy or radiative budget. So people try to model, radiative processes from these different types of clouds. There's a lot of uncertainty that goes on there, and a lot of it just stems from a general lack of observation. So most observations that we've had, especially in the last 20 to 30 years, have been space-based remote sensing instruments with a few field campaigns here and there to kind of rectify those deficiencies that we have there. But ultimately, we just need more observations, to inform and assess model output to get to the answers that we're looking at here. Here's a plot from the IPCC fifth assessment report here. So again, if we think of radiative effects as long wave, short wave, or just in the net, again, we look at the subtropical oceanic basins here. This is I guess a bias in watts per square meter comparing observations to models here, and I guess it goes without saying that the biggest biases tend to happen in the subtropical oceanic basins here. Happens in the southern hemisphere too, but again, this is mostly because there's just not enough observations there. And another, thought here, this is from April's recent paper actually, so fairly, there's a lot of numbers on here, but I'll distill this down to, the Stratocumulus cloud aspect. So, this framework that we think of in a climate perspective, we have incoming solar radiation, and then, that all gets distributed, to clouds, sensible heat, latent heating, evaporation, and there's a lot of other processes that affect, the radiative balance, and then what happens in a heating perspective here. So all these yellow boxes here that I have specifically point to stratocumulus clouds. Now, what I found really cool about this particular figure here, also an adaptation of an earlier paper here too, that, there's 9 different types of clouds here, and all these numbers here represent either a flux or a heating, and stratocumulus clouds are the second, biggest contributor to a lot of these numbers that we see here. So this just adds more context to why we need really good observations here, just in general, for stratocumulus clouds, but just clouds in general, frankly. So the aerosol aspect. So again, we could talk about aerosols, pretty much anywhere, but the focus of this talk will be on the Southeast Atlantic Ocean. Now, what you see here is an International Space Station view of the South African continent here. So during the biomass burning season, which typically starts late June, early July, fires come about, summer wildfires, but most of them are actually from farmers out there who just need a place to get rid of their trash, and they start a lot of these fires here, and a lot of that biomass burning aerosol, you get so much different stuff in there, and that in itself is a fairly extensive research project. But a lot of this aerosol just gets lofted up, and then it gets carried out into the Southeast Atlantic Ocean by the subtropical easterly jet, in the southern hemisphere there. We'll show this a little bit more clearly on a couple slides here, but I took this picture actually on the aircraft that, when we were in between the, just above the stratocumulus deck, but below the aerosol layer here, and you can clearly see, maybe a little bit more clear on my computer as I see it here, but we see a very distinct smoking cloud there. So the clouds are very clearly almost nearly touching here, in this case the biomass burning layer above that, and again, this just adds context to what does this actually look like, and whenever we're trying to measure these types of processes with remote sensing instruments that might have vertical resolutions, more than 1 to 200 meters or so, these gaps can sometimes be less than a couple hundred meters. So we really need good observations to really know this in order to formally assess what those impacts are. So I alluded to field work. There's me kind of standing in the back there. This is from, the Oracle's field project, I guess. This was a 5-year NASA field project. We went out into the field for 3 of those years, 2016, 17, and 18, August, September, and October, respectively, to collect a really large, robust data set with the end goal of rectifying this deficiency that we have in Cloud-Aerosol-Precipitation Interactions, radiative impacts, precipitation processes, you name it. So when they put together this graphic here, again, this kind of more clearly shows the, what actually happens here, the biomass burning layer. If you imagine this is Africa here, it gets lofted up, transported, and then just over time it subsides into the stratocumulus deck that's out in the Southeast Atlantic Ocean, and then you just get a whole different hodgepodge of just things that are going on here. You get cloud thickening, cloud burn-off, how are the aerosols interacting with that? You have the issue of marine boundary layer aerosols, and we have, I think, on this graph alone, there's about 23 to 24 different instruments that are being used just to look at little aspects of this. So when I can't stress enough how complicated the problem is, in this regard here. So my, I guess, role in this was running the radar here. So here's a nice picture of the radar, what it looks like inside the plane at least. We have all the machinery there. These are the KU and KA, and this is actually the box that runs the instrument that I took most of the data for. So for people, I guess, the more senior scientists in here, you might think of the APR-3 radar as a airborne prototype of the trim precipitation radars, which are KU and KA band channels, and the cloud profiling radar, which is a 95 gigahertz W-band radar. And, for this particular project in oracles, what we want to do is, support the level 2 and level 3 science objectives, since in oracles at least, the level 1 was mostly aerosol direct effect stuff, which is mostly LiDAR and in situ aerosol measurements. So this is just these are the 3 main science questions that were outlined by the oracles campaign to, for which the radar could support. So we have investigating the sensitivity of cloud structure and condensate to aerosol-induced heating. We have, measuring the changes in cloud microphysical properties, precipitation as a function of aerosol mixing into the boundary layer, so in other words, the Stratocumulus deck, and investigating the sensitivity of cloud structure and condensate to aerosol-induced suppression and precipitation. So for this project, again, can't do everything, so we focus mostly on these last 2 objectives here. So how can the radar be used to measure changes in cloud microphysical and macrophysical processes, especially with, having precipitation aerosol data, and also aerosol-induced precipitation suppression. So from these objectives, keeping those in mind and keeping in mind my own personal research interest here, tying back to the whole global climate aspect here, we distill this into 3 main science questions, and we'll talk about them individually through the rest of this talk here. My first science question is, since, again, this is a relatively new data set here, I created pretty much the entirety of it. What are these retrieved precipitation rates from airborne radars? And kind of extending that a little bit further, because we measure pretty much everywhere in the Southeast Atlantic Ocean, what environmental controls dictate those precipitation rates? Second question here, again, doing the whole airborne remote sensing synergy that we have, how do we use multiple airborne remote sensing data sets to study aerosol-induced precipitation suppression, and is there evidence of that? We find a little bit, thankfully. And third, what are the relative roles of Virga and surface precipitation to the local energy budget? Now, this last question, kind of stemmed from after I completed the work for the first science question here, because, I wanted to, perhaps naively, back in 2016, surface precipitation, meant hitting the surface. But when we started looking at these, thousands and thousands of radar scans here, it's like, wow, this is clearly precipitation, or would qualify as precipitation, but it's not reaching the ground. So there's a lot of Virga that we saw in this data set here, and I'm like, that has to be doing something, like from an energy perspective, what have people saw here? And, when I tried to dig a little bit, that wasn't really a whole lot. So I thought, wow, this is actually kind of interesting here. So, okay, just a second. So now, let's quickly discuss, that's the Saharan air layer, by the way, not the aerosol back here, but anyhow, there's Simone, he actually runs the APR-3 radar out of the Jet Propulsion Laboratory, kind of this fancy setup here that we had a nice chance to use here, but yeah, you can see the radar scans kind of in real time here. But this particular radar, again, there's 3 channels. We use the W-band channel because it's going to be most sensitive to the types of clouds that we saw during oracles, which are very light cloud and very light precipitation. So light to moderate, heavy drizzle. We did find some light rain to moderate rain occasionally, but by and large, it's mostly just light drizzle to light cloud cover. The precipitation retrieval method. So what I've spent probably half of my PhD on was trying to develop a retrieval algorithm, that was modeled specifically for CloudSat's 2C rain profile, but specifically adapted for use with airborne sensors. So any good W-band radar with a surface backscatter measurement, you can retrieve precipitation properties if you properly assume everything else. Don't have a whole ton of time to discuss that, but the second data set, I guess, that we use here, this is a support to the radar data set that I have. This is the research scanning polarimeter. So the main purpose for this particular data set is, being a passive microwave radiometer, we can get really good, robust measurements of cloud effective radius and cloud optical depth. So in using those two measurements, we can use that in conjunction with the radar data to get good, reasonably accurate and robust retrievals of precipitation. So, there's kind of two versions of the algorithm, one which has already been published, and then the second one which includes the cloud optical depth constraint here. So, very quickly, so if we imagine our measurements here very quickly, so we have, Z1, Z2, that would be a reflectivity measurement. We have profiles of reflectivity, we have a cloud optical depth, and a path integrated attenuation. So the reason we need attenuation is because, especially for anything starting with like moderate to heavy drizzle, there's going to be several dB of attenuation that happens. So we need that to correct the surface precipitation rate and the maybe lowest 2 to 3 bins of precipitation if they're occurring there. We feed a retrieval algorithm, which is we forward model a reflectivity, we take the observations of reflectivity, and then we constrain it with the cloud optical depth supplied by the RSP and the path integrated attenuation from the radar. And we use appropriate models, one for optical depth, one for path integrated attenuation to get a full profile of rainfall rates. So for every Z, there will be an output R, and then using the cloud optical depth in conjunction with, the radar here, which, can't see like clouds, we get a cloud water path retrieval. So those are going to be the main two that I use here. And then implicitly here, too, I didn't put it on this particular slide, but there's cloud water path that's retrieved, and the radar specifically is for rainwater path. Yes, John?
What is cloud water path?
Cloud water path is the total vertically integrated cloud water content from cloud size droplets only.
Okay.
Yes. And rainwater path would be, anything from raindrop sizes larger. 50 microns or so is the threshold for that.
Okay.
Do you have a question?
How is the optical depth being determined?
Modeled or observations?
Well, observation.
Observation. It's directly observed by the
Satellite?
the RSP.
Oh.
Yeah. Yep. So again, the synergy aspect here. Okay. So again, since we're talking about precipitation, anyone that's ever studied this will understand when we're trying to invert reflectivity into precipitation, there's going to be a heck of a lot of uncertainty with this. So need to make a statement about that. So from this particular data set, we know that for higher rain rates, that those uncertainties are on the order of 50 to 100%, and they exceed 150% or so for the largest rainfall rate, or smallest rainfall rates, excuse me. So being less than 0.01 millimeters per hour, or roughly what we saw probably earlier this morning when we were all herding into the building here. So that's very light drizzle or so. Main sources of uncertainty from precipitation are going to be from the drop size distribution, and then occasionally attenuation effects from gas and other things where we don't need to discuss that a whole lot. Uncertainties from rainwater path are about 30 to 100%. Cloud water path uncertainties are actually pretty good because from the RSP, the cloud optical depth uncertainty is about 7% and effective radius is 5. So the main reason we get 25 to 30% is because of the assumption that we have to use with the cloud water path to distribute as cloud water content through the rest of the cloud. So let's show an example of this. So this is the only slide, I guess, where I show kind of what's a typical test case before we dump everything into broad, large-scale statistics here. So top reflectivity panel here. There's 5 panels here. We have altitude for the first 4 panels. This is from 0 to 3 kilometers, and this scale is from 0.01 to 1,000 grams per square meter. This is a 2-minute scan, of a very typical average case that we saw during Oracle. So very, like I said, you look through 100 of these, you'll see a bajillion of these because that's exactly what we saw. Top panel is uncorrected reflectivity. Bottom panel is corrected reflectivity. So again, since a lot of these reflectivity measurements are on the order of -20 to -5 dBc, again, we don't see a whole ton of attenuation for very small reflectivities like that. So naturally, they match pretty well. Cloud water content in the middle there. So in this particular case, the cloud optical depth supplied by the the RSP were on the order of 10 to 20, so the cloud water paths, exceed 100 to 150 grams per square meter. So we're distributing a lot of cloud water path into, basically, 200 to 300 meters or so of cloud where we expect it to be. So, find that to be interesting. We don't do a whole lot of study here on the profiles of cloud water content per se. But most important one though that we look at for my work here are these profiles of rainfall rate, because I guess when I say I'm going to use rainfall rate, we're going to look at the maximum column rainfall rate, because this tells us, okay, it's either going to be surface precipitation or it's going to be drizzle from somewhere else. And that's, I think, the best way to aggregate these statistics and just look at it generally speaking. One other thing I found that was pretty interesting here was the rainwater path from, a lot of these cases here. And in many cases, rainwater path, derived from the APR3 observations, tends to be, in the order of about 0.01 to 1 to 10 grams per square meter or so. So there's a lot of really small rainwater paths in here relative to the cloud water. Okay. Second to last data set, I guess, that we use for looking at stuff is the high spectral resolution second generation. So this is the data set that actually supplies us our aerosol data. So we need, basically something to inform that. I'll dive into this more when we talk about the second science question that I have, but we know that we can use this for aerosol contact versus non-contact, above cloud aerosol optical depth, and also a very nice and unique aerosol classification scheme, to make sure that we're actually looking at smoke and not other things, I guess. And finally, it would be really hard to do any kind of cloud aerosol precipitation analysis without some meteorological context. So we have to include atmospheric state data somehow. We use ERA interim, for this particular study. Downloaded this probably about 2 years ago or so. I know the ERA 5's out. Updated versions might include that. But what we look at mainly is estimated inversion strength and sea surface temperature, for science questions 1 and 2 in here. Estimated inversion strength, this has been around for about 15 years now, I would say, 10 years I guess maybe. Very similar to lower tropospheric stability, but it also accounts for temperatures and the fact that the environment is mostly moist adiabatic and subtropical conditions like the ones that we see here. So this is, I think, a good metric for saying, when we're at 0, for example, anything less than 0 is going to imply unstable conditions. So there's no inversions versus larger estimated inversion strengths where we might see 5 to 10 kelvins or so, basically saying that's how strong the inversion is. Probably should have put a cool graphic here.
What's LTS?
Lower tropospheric stability.
And that's like a standard atmosphere or something?
Yeah. Potential temperature at 700 hectopascals to the surface.
Oh, so it's measured at that location?
Yes, and it's derived from the ECMWF data.
Okay.
Yes. Okay. So a very quick summary. Our airborne remote sensing perspective, stems from radar data, passive microwave data, and LiDAR data from the APR3 RSP and HSRL instruments respectively, and we account for environmental controls. So that's just a general basis for all 3 of the science questions, I guess, that we ask here. So let's get into the fun stuff, all right? Let's ask our first science question. What are the retrieved precipitation rates from airborne radar, and how do environmental controls possibly explain these variations here? Okay, so in order to get some context for precipitation rates, let's ask ourselves, well, where are we taking these measurements? So here's a graphic I made. This is kind of a cleaner version of the one that's on the ESPO website here. This shows the Southeast Atlantic experiment area and our most typical flight tracks here. I have kind of, the bases are located, one at the southeast here. This is Walvis Bay, Namibia, where we did the 2016 experiment, and then there's the 2017 and 18 experiment base, which was in Sao Tome and Príncipe, so the capital city of Sao Tome, basically. In 2016, a lot of the flights, I guess, we would, we'd take off at their, Walvis Bay Airport, and we would fly, southeast to northwest or so, and we would sample areas down at the very, southeasterly extreme of the Stratocumulus stack into the middle of the basin, at about, 5 to 10 south or so. I mean, we did get a little bit higher than this somehow, but typically we turned around starting at 10 south on that flight track. In 2017, got kicked out of Namibia, unfortunately, so we had to move to Sao Tome. And from here we flew a lot of flight tracks from basically the equator down along the 5 east longitude line and out and back. And I mean, there were several flights that kind of went out. They would resample the air masses a couple days later or so, or they would fly south and then west to Ascension Island, which is where we occasionally did a suitcase flight or an out and back flight, I guess, to, kind of get, properties on the furthest extent of the Stratocumulus deck here. So just already, thinking about the flight tracks alone, there's going to be some pretty big differences in the environments that we see here. So obviously, there's going to be warmer sea surface temperatures near the equator compared to near where it is here in Walvis Bay. And unsurprisingly, most of our flight tracks sample very different aspects of the basin here. So the good news, I guess, with sampling in this regime is that we literally have a data set that covers pretty much the entirety of the Stratocumulus deck. But in that context too, the estimated inversion strength, which is again the main variable that I choose to look at for this work that's presented in this talk, it's really stable in the southern part of the basin here. So these inversions, have they're 5, 8 ton kelvins, sometimes larger, and near the equator, in the mean sense, they're generally stable on the order of like 1 to 3 Kelvin or so. But again, mean statistics also implies that there's a lot of negative EISs, so a lot of unstable environments in here. And this also kind of weeds out a little bit, some of the day-to-day synoptic variability that may happen. But by and large, there were only a couple days worth of data where, we had actual like weather systems that disrupted the typical day-to-day flow here. So for our purposes, they're mostly consistent there. And here's just another way to look at it. Here's these are flight tracks, beginning of the flight, middle of the flight, end of the flight, and what type of EIS regime did they fly in. So in 26, again, extremely stable. In 2017, not as stable, and the same was very true for 2018, although not put on this particular plot here. So that leads us to some of the cloud properties we saw. Probably one of my favorite figures here. So this is a contoured frequency by altitude diagram of all the reflectivity profiles, model reflectivity profiles, mind you, the ones that are attenuation corrected for the 2016 and 17 experiments. So first thing that should immediately pop out is that indeed the clouds were generally a lot thicker and a lot taller during the 2017 experiment. This little bar amount here, I think people might know this, are cases where, when we had, light to moderate drizzle, the algorithm has a tendency to correct, from, starting about 0 to, 10 or 15 dBz. So we actually saw, quite a bit of, light rain, I guess, in 2017. Again, same is true for 2018. But 2016, wow, these clouds are really thin, really shallow. And again, this has a lot to do with the sampling environment. I think another, and perhaps the most, when we look at a contour diagram here, it's like, okay, well, most of the points are centered where at exactly, and in both years, actually, it's between -20 and -15 dBz. So these are just either extremely thick clouds, well, thin to thick clouds or whatever, but just on the periphery of being drizzle or precipitation, so like at about -15, which is what most experts agree to be the threshold for drizzling versus non-drizzling. And not unsurprisingly here again, differences in rain rates for between the 2016 and 2017 experiment did show up here too. So the first thing I think, which is probably the most important thing to stress, is that almost all precipitation rates retrieved from oracles were extremely light, so less than 0.01 millimeters per hour or 1/4 of a millimeter per day. So very light drizzle. These statistics, I guess I should mention, are only for cases where the APR3 actually saw a cloud. So this is cloudy statistics only. This is, we're not area averaging or doing anything like that here. Looking at 2017, you'll notice that as we go to the right on this graph here, so to higher rain rates, so where we actually get light to moderate precipitation, closer to, about 8 to 9% of all the retrieved precipitation rates were in the, what we would consider, I guess, rainy category, so like 25 millimeters per day. So something very light here. And also worth noting too is that, in 16 and 17 for a lot of these profiles, about 1/3 of all profiles were just clouds only. The rest of them had at least some sort of Virga. Although in 2016, interestingly, a lot of profiles, I guess, were, had retrieved precipitation rates, but the Virga fractions here were very large. And again, that's kind of where motivation for the last science question came into play here. So a lot to digest there, I'll continue on here.
But your CFAD diagrams
Yes.
incorporate the average of all of these things. So
Yeah.
there's no segregation, right? You're not looking
No.
at, okay, there's no
Yep,
segregation.
no segregation, not yet.
Did you do that in the background, or are you going to show us that?
I am not going to show that.
Oh, okay.
But yeah, I mean, there's most of my looking at that was just like case studies, like taking the full curves.
Yeah, okay,
And,
okay.
yeah. Yeah, and that's also summarized in like the tables, I guess, that I have in the published paper too. Okay, so again, just a quick summary here. Again, the big thing is that most precipitation rates were light, and the sampling environments were very different. So now, let's get into a really fun question here. You know, it's kind of sad, I guess, that I can't do a whole ton more, so I'm gonna add a little extra motivation here for this particular question, which is using these multiple airborne remote sensing data sets, is there evidence of aerosol-induced precipitation suppression? Okay, so let's give a quick background, because this is, yeah, again, there's a lot going on here. The two landmark studies, I guess, for aerosol-based precipitation suppression, you know, stem from Sean Toomey and Bruce Albrecht. You know, in '74, it says increasing aerosol should lead to an increase in the total number of cloud drops, where cloud drops overall are smaller, so a larger number of smaller droplets. And then in 1989, you know, Albrecht in his landmark study found the collision coalescence efficiency of drops should be reduced, you know, which would reduce the onset of precipitation. So there's a precipitation suppression, you know, just possibly occurring from the presence of aerosols here. But in order to actually like tease out, is this an actual process? It's very difficult because there's a lot of other atmospheric drivers that have to be deconvoluted first, and there's, you know, a couple studies, you know, Allison just did a recent one here, kind of showing that too. So, you know, talking again about atmospheric drivers, atmospheric state, environmental controls, let's go revisit this for a second here, but let's look at everything here. Let's look at rainwater path, cloud water path, and our maximum column rainfall rates here. So just in general, again, this is just more what do we kind of expect here. You know, going from, you know, sea surface temperatures measured, you know, for anywhere from 299 to 304 Kelvin. So again, representing most of our data set here. So as a function of sea surface temperature, again, we see rainwater path generally increases. The amount of cloud water path, I guess, you know, yeah, there's some variability there, but by and large stay the same. And we should expect larger rain rates in regimes where there's, you know, larger sea surface temperatures. So I'll add too that these are log scaled as well, so the lines are there purely for visual reference. They're not an actual like, you know, regression or anything here, but just for, again, helping out. But when we look at estimated inversion strength, we see the opposite actually. We see that, you know, for increasing stability, you know, these really large rainwater paths, you know, exceeding, you know, 100 to 1,000 grams per square meter generally go down. Cloud water path, kind of similar here, I guess, too, but again, a lot of the cloud water paths, you know, on the order of 50 to 200, and we still even see that even for really large estimated inversion strengths. And rain rates as a function of EIS are, again, it's very similar here too. So the higher the stability, the lower the rain rate that we see here. So this gives us really important context for assessing the rest of the, you know, the aerosol question, I guess, that we're going at here. So again, this kind of summarizes everything here with increasing SSTs, everything increases with increasing EIS, everything decreases. Slightly better correlated, but I don't want to say too much about that just because.
Can I ask another question?
Sure, yes, John.
Isn't there a correlation between sea surface temperature and estimated inversion?
Yes, there is. So I think the reason I think they're probably slightly better correlated in this case is because, you know, it's partially included, I guess. You know, it's, you know, we're talking about the temperature of the surface, and
Okay,
yeah.
so I'll ask you later. I just want to know why look at these two, all these three variables with respect to those two environmental conditions, since they're so strongly related to each other. So we'll talk.
Yeah, so yeah, it's probably a little bit of covariability going on there.
Yeah,
but
that's what I guess.
again, yeah, you're absolutely right about that. So, okay. So now I would like to introduce here, you know, we can look at cloud water path and rainwater path, and I did look at these individually, but I thought it would be more instructive for this particular case to look at the cloud water path to rainwater path ratio. So in other words, for every unit of rainwater path, how much cloud water path is there in these given clouds here? So this particular box and whisker plot, so we have for the entire experiment, and then for large and smaller rain rates here, just to say, okay, like what kind of ratios should I expect whenever we see, you know, light rain, heavy drizzle, et cetera, versus either very little drizzle or extremely, or close to none at all. So obviously for these statistics to be possible, there has to be at least a little bit of rainwater path. So we don't have like purely cloud only necessarily, but it's still a good measure to use, I think, for this particular work here. Now, the ratios of cloud water path to rainwater path, just in a statistical sense, you know, they're about, you know, 20 to 80 units or so, but when we eliminate, any cases where there's heavy rain potentially, these ratios can get as high as 200 to 1. So that's a lot of cloud water path per unit of rainwater path. So I thought that was just really interesting to me, and just to calibrate myself to what I might expect whenever we partition our results from, are there aerosol interactions versus is there none? And by that, we have to come up with a more robust definition here. So this is, the threshold, just after looking at a lot of the data qualitatively and, just doing that, we have to figure out, are the aerosols, or is this biomass burning layer actually touching the cloud versus is it not touching the cloud? So using the HSRL data, we come up with a threshold using the backscatter coefficient data. For this particular case, we set it to 0.25 millimeters per steradian. This is directly suggested by Sharon Burton, one of the PIs on the HSRL team. And then secondly, we look at above cloud aerosol optical depth. We make sure it's extremely low, so less than 0.01. We keep it that way too because there's always going to be a chance, well, okay, there's going to be aerosol somewhere in the column. It's never going to be non-zero necessarily. So we want to use that as a screen. And then we also want to look at the above cloud aerosol optical depth to where, we want to make sure that, since it's a cumulative quantity, so like the further down you go, the more it increases. But at a certain point, if it's away from the cloud, the slope of the aerosol optical depth will either, it'll be really close to zero in that particular case. So a little bit of redundancy here, but there's really good reason for that. So now let's ask ourselves, well, okay, we have a contact definition. How much does this actually happen here? So here's a good case, I guess. This is a paper or the plot that I included to support two collaborators down at the University of Miami. They are looking at HSRL curtains, along the 5 East track here, and I thought this is a really good example to show that, we see a lot of, we see heavy precipitation right here, on the order of, 10 to 15 or so dBz, but a lot of Stratocumulus, a lot of light Virga, and a lot of aerosol contact. So 100% of all the APR3 profiles in this particular case tell us or show us that there is aerosol contact going on here. What about cases, I guess, where there might be non-contact, So again, why we come up with thresholds here. So in this particular case, there's clearly some aerosol here. There's a lot of aerosol, once we get to our 9 to 10 of this particular transect here. And then by the end of the flight here, we're talking, okay, this aerosol layer goes away here, it's decreasing, but we see a couple gaps. And, this lends some confidence, I guess, at least for, what constitutes aerosol contact versus aerosol non-contact. We want to make sure that there's smoke that's in contact, so we're more likely to get those fine mode aerosols that actually do something to the clouds that promote the Cloud-Aerosol-Precipitation interactions. There's a lot of recent work that shows that this is the case. And again, the above cloud aerosol optical depths, a lot of these are much less than 0.1, but when we get over here, it's a lot of aerosol here. This one, I think, is particularly famous because, they call this one the bacon layer case because the aerosol backscatter coefficients in this particular case looks like a strip of bacon. But using these definitions, we find that 86% of all APR3 profiles were in contact with an above cloud aerosol layer. So again, we've built up a lot of definition here. It's going to distill down to about 2 slides here, I think, that include all the information we need. But we can't do this without mentioning, we don't know, at least yet, how long were these aerosols in contact with the Stratocumulus cloud layer. So in other words, when we say contact, has it been contact like instantaneously, which is the assumption that we have to work with here, versus has it been in contact for 3 days, 5 days, 8 days? Sometimes that's true, actually. So we have no clue, at least yet, again, what the life cycle is. And we also know that there's also existing ring bounded layer aerosols. So like there's possibly smoke in there that's already interacted. There's also sea salts, et cetera, that might have occurred there. So this all comes down to a table here. So now we have our contact definition. We know, there's aerosols in contact versus aerosols not in contact. So what do the cloud water path to rainwater path ratios look like in addition to the maximum column rain rate? So again, showing just these two because the rainwater path to cloud water path data suggests, pretty much exactly the same thing here. But in stable environments, the contact ratio is 77.6 units of cloud water path to 1. versus 36 in non-contact. So when it gets in contact, there's a lot more cloud water path per unit of rainwater path here. So naturally, there was a corresponding decrease in the amount of rainwater path, I guess, that happened too. Again, not shown on here, but the more, if we increase our stability threshold of an EIS2 greater than 4 Kelvin, this becomes even more exacerbated here. We're talking 91 units of cloud water path to rainwater path. And, if we take the means of these data here, the means of the contact cases versus the non-contact case, we, state a hypothesis here saying, the mean values of these ratios and the rainfall rates in contact versus non-contact are not statistically significant. These are very statistically significant. These are, T values, on the order of, 5 to 6, exceeding the critical value, and, P's of like, 10 to the minus 5 or so. Rain rates, though, I don't want to say disappointing per se, but didn't correspond quite as well. So, again, in stable regimes, we see, a decrease, non-contact versus contact, so there's clearly something going on here. What that is, unfortunately, we didn't get too much time to explore here, but, there's very much a decrease, in non-contact rain rates versus contact rain rates. So while these were not statistically significant in the case, the, these lower p-values suggest, it lends confidence in some ways, but, you just can't say, that, that's statistically significant, I guess. So, investigating that science question, we see, looking at cloud water path values, again, since this is the first time, we've generated this data set, we see typical values of 5,200 grams per square meter. We've contextualized the amount of rainwater path, and we do see some statistically significant differences between cloud water path and rainwater path. So this is kind of where this work ends and where there's a little bit more to be done, to investigate specific questions related to, for example, precipitation susceptibility. We can test cloud albedo. We can really do, the rest of the gauntlet, with now freshly available measurements from the RSP to make that possible. All right, we have about, 8 minutes to wrap up here. There should be plenty of time. So now, let's bring this back. So we've had a lot of talk about what are the typical observations, what are the environmental controls, what do aerosols do, and now, what about the energy budget here? So, a little sad actually that I didn't get to do, investigate this too much in the context of, aerosols versus non-aerosols, but I had a really basic question, I think, to kind of round out this last part of my dissertation here. So, if there's a lot of Virga, there obviously is a lot of evaporation. So, and in a latent cooling context, that means like there's going to be a really big latent cooling sink if this much Virga is actually happening here. So that's kind of the motivation for that. But how to actually define what is evaporation? What do we use in evaporation rate? And upon a lot of discussion with Tristan, Ann Fridlin and Giss and a couple others, we decided on a definition of maximum column precipitation rate relative to the surface would be an evaporation rate. So when we think about Virga, then that means everything evaporates since the surface rain rate has to be 0. Obviously, assuming too that it's not just that one bin, but we use about 200 to 300 meters or so to make sure that there's enough distance for it to evaporate. That's also based on modeling studies. And for surface precipitation, that's basically the maximum column rainfall rate minus the surface precipitation rate. So effectively, the difference there. So if it goes to 0, it's Virga. If it's not 0, so. So thinking about this a lot, now we go a little bit further here. So how do we define an evaporation flux? Multiply by density of liquid water times the latent heat of vaporization. You'll find this in the literature too elsewhere, but this will give you a unit of watts per square meter, so we can know the evaporation flux that happens, with evaporation. And we can think about latent heating and cooling also too. So using, this is out of Grant's textbook here. For 2 prescribed levels, you can, describe a heating rate, is the difference between, 2 fluxes at 2 different levels of the atmosphere. So if we modify this for just evaporation, we know that, we use the cloud-based height, or maximum column rainfall rate as that assumption relative to the surface. We can get heating rates relative to that too, just from evaporation, which, again, we're really, diving into some, fine details here. But, both of those are used, they're about the same, I guess. The only difference between, latent evaporation flux and latent cooling rate is the dependence on altitude. So, let's take a quick look. Again, we need to, think about how often did this actually happen here. So now, I divided this again, so our x-axis here being evaporation rate in millimeters per day, cumulative frequency on the y-axis here. Now, I chose number of points as opposed to 0 to 1 just to show the detail here in the middle here, but also to show just how few surface precipitation rates we actually had from the Oracle's campaign here. So our green and blue lines are cumulative frequency distributions of surface rain rate with low estimated inversion strength, meaning unstable conditions, and high estimated inversion strength, meaning stable conditions. Same is true for Virga. We have a lot more Virga profiles under low EIS conditions compared to high, but again, there's a lot happening there. So this already tells us something too. There's a lot more Virga than there is surface precipitation. So, you know, kind of getting at that, so then what must the evaporation rates be in that particular case? And then I'm like, okay, the opposite is actually true here. So again, we've contextualized these results in terms of, you know, stable versus unstable EIS, but also just in terms of the overall campaign, since just in general, we see, you know, for surface, you know, 2.3 to 0.253, 3.74 to 1.138, you know, that's over 10 times more evaporation that happens from surface precipitation relative to Virga. In a campaign sense, these numbers are almost exactly 10 times that amount too. So, surface precipitation, you know, in the entire column clearly contributes more evaporation flux, therefore more latent cooling. But again, we saw this again, so I'm like, let's take a final look here. Take a look and see that, you know, for most surface precipitation rates, now that we have the 2018 data to work with in here, only 8% of all our available cloudy sky profiles actually have surface precipitation. And once we account for, again, environmental stability, so positive, you know, EIS is, you know, this is for like marginally stable and unstable, there's just a lot less surface precipitation. Again, this is just based on what we have from the reanalysis data sets here. So then this leads to, you know, how much does it actually contribute then? So if we know that surface precipitation is only about 8% of all the cases and less than 2% in high EIS cases, but Virga, by contrast, is over 60%, you know, in most cases, you know, 50 to 60% or so, we can think of the contribution of total latent heating or evaporation flux, you know, in terms of, you know, the total available cloud fraction, I guess. So our contribution of Virga or surface precipitation to the latent heating or evaporation budget, I guess you could think of that, would be, you know, your cloud fraction. So you imagine, you know, any latitude by longitude degree box, you know, if there's 100% cloud fraction, 50% cloud fraction, you know, it's fairly robust to say, I guess, or it is, you know, we find that, you know, Virga still, you know, happens, you know, 50 to 60% of the time, regardless of cloud fraction. So cloud fraction over a given area, not as important here. So we just need to know the precipitation fraction of Virga, or precipitation in this case, and the latent heating of Virga and precipitation in that case. So when we actually account for the fraction of, you know, surface precipitation relative to Virga, it's actually a ratio of about 2 to 1. So it's still about twice as much heating in the Southeast Atlantic, you know, happens from surface precipitation relative to Virga, even though it's 10 times that. So what this really says is it's still really important to think about Virga, you know, in addition to surface precipitation. And I don't think I've mentioned this yet either, just with these observations that we have, but, you know, the fact that we're flying, you know, W-band, you know, just above these clouds, we're able to get, you know, full curtains of really thin stratocumulus clouds, you know, that are otherwise unavailable, you know, by current, like, spaceborne remote sensors like CloudSat, for example, which, you know, are blind below 750 meters. So the fact that we can get this detail enables more study like this. And, you know, to kind of, you know, we know this, you know, for the Southeast Atlantic, there's two more things, I guess, to be done with this, and this is where this work ends. We need to know how this changes as a function of aerosol, you know, doing a similar analysis to what I did for science question 2. And also, we need to look at other oceanic basins. So we actually have similar data sets for the Northeast Pacific Ocean and the Southeast Pacific Ocean from the vocals and the CSAT data sets. So we can take a really good look to say, okay, now that we have data sets in clean, you know, stratocumulus layers, we can actually compare it to an aerosol polluted case like, you know, the one that we saw almost all the time during oracles. So to quickly summarize, we've retrieved precipitation rates from the 16 campaign, found that they were different for both 17 and 18. Didn't show that for 18, obviously, but definitely happened there. I have that as an extra slide if anybody wants to see it. The sampling environments were definitely different. We found some evidence based on our contact versus non-contact analysis that, the cloud water path and rainwater path, changed significantly when aerosol was present. More work obviously to be done to distill that further. And finally, again, just kind of a question that I thought was interesting, we find latent cooling from evaporating Virga is much less than that from surface precipitation, but given the frequency of Virga and how much we saw it, it's very important to look at. So, we have 4.5 years to do this work, and there's still, this is like the 3 biggest points I guess I could think of for more work, to kind of extend upon this. The cloud water path I mentioned is a very new product, but thankfully, there's other, collaborators from Oracles who are working on this now, the Cloud Probe Group specifically from North Dakota and University of Oklahoma. We'll be validating the cloud water path and water path in statistics to see how good this retrieval was relative to, what we measured in situ. I mean, there's obviously going to be sampling limitations from the in situ measurements, but they should still give us a pretty good idea, especially with the cloud water path, to see that did we distribute the cloud water content appropriately throughout the cloud. Secondly, especially with the number concentration data now available from the RSP data, we can actually really look now at precipitation susceptibility. We can take changes in rain rates as functions of number concentrations derived from the cloud top. And finally, I kind of already mentioned this, but looking at, this airborne remote, this airborne-based algorithm, that I've developed for my PhD, we can apply that to other data sets, and we can investigate science question 3 for that. References here. Now, because it's a defense, I have to acknowledge, pretty much everybody here. First and foremost, I got to thank Norm Wood. I don't see him in the audience here, but without, I guess, his help, he helped me really get off the ground. He was the one that, I guess, took the base, the black box of the algorithm that was applied for CloudSite, made it, work on my desktop, and he's like, okay, basically the rest was up to me with that. But basically this project doesn't happen without his help. So he gets my first acknowledgement. Secondly, beat the heat. Obviously we can't, I wouldn't have been able to do most of this work as quickly as I could, especially for some of the times where, I shut down our servers from, parallel processing, experiments gone wrong. I need to especially shout out my office mates, Juliet, James, Tobiah. I don't think, I guess, on a more personal thing here, when you're, I guess, in grad school, for 3 to 4 years or so, you're spending literally, 6, 8, 10 hours sometimes with the same people. So in many respects, they become family to you, so, and they definitely see me on, really good days and also really bad days. So to all you, the 3 of you, I appreciate you very much. The rest of the LEC group, again, I've needed to lean on people for a lot of support, obviously. Ann, Julia, Kate, Ethan, pretty much everybody else, Marion, for tech work too. Again, just way too many, people to thank here, I guess, so, which is why I said pretty much everybody else I've met in this building too, from 2016 until now. I really feel at home in this department. I feel like I can, just go around, talk to people, ask advice, and just, it's a really good place, and I am really thankful to have been here to do this work. So my last 2 acknowledgements, my committee, obviously, you had to read a very long paper in a couple weeks, and also, sit through many meetings with me, helping me guide me along the way, and, really appreciate all your help and support there. And finally, Tristan, this has been an absolute dream project to work on. I've been very enthusiastic about it, even realizing, there's, questions lead to more questions, and, so I appreciate you taking a chance on me and getting to this point. So with that, thank you, everybody. I guess.
Okay, you have the questions for Andrew?
Juliet?
Yeah, so I may have missed it, but how heavily attenuated was the the radar signal due to some of this precipitation?
In a statistical sense, I would say the average was maybe 1 to 2 dB or so, and most of that's going to be from cloud water content, actually.
Okay,
Yeah, so it was, the largest attenuation, very rarely happened.
okay, and so did you correct for that in your?
Yes.
PC?
Yeah, so I guess there was a two-step correction. One was we did a gas attenuation correction, so where we, again, I didn't include this up here, but the atmospheric state data that we had was used to inform a gas attenuation correction model. So most of that was actually, probably, anywhere between 3 to 7 or 8 dB, depending on where we were. So closer to the equator, there's more gas attenuation by water vapor, and, further south, there's that. And then there's also the PIA model, I guess, which corrects for the hydrometeor attenuation. So it's robust in that regard. John?
Yeah, really interesting, a lot of aspects. One thing I'm curious about is, what about tendencies in the estimated inversion strength and how they might be related to synoptic scale processes? Because one of the things that comes to mind for me is that your smoke layer, it could be moving up and down. And if it's moving down toward the top of the stratocumulus, that's almost certainly an environment that's promoting increased stratification. And yet at the same time, it's increasing the number of CCM, potentially.
Yeah.
So you can, some of these things might be compounded in certain directions. Have you thought about that, or is there any way to do that with your observations?
Yeah, I think so too. Definitely. I think I've told you this, Tristan, before, but like one thing I definitely want to look at too is, pressure velocity, or omega, I guess, from the ECMW free analysis data, to kind of get a second look at, okay, there's definitely subsidence going on here, for example. And the second thing too, I think I very briefly mentioned this, in the talk, but the contact time, I guess. So we need to, I guess there's more work, a lot of work actually, to be done to do, I guess, for example, back trajectory analyses, to see where did that air parcel come from and how long, did the aerosols actually contact it? Because there's a lot of cases, I guess, too, and you kind of saw one of the cases too, I guess, in the paper that got accepted last August, but there was a low, I guess, that got cut off, and then that totally changed the typical wind direction. So the easterly jet was, kind of pushed northward a little bit, and a lot of clean air was getting into the boundary layer there. So, a lot of, definitely thought about it, but it's really complicated.
Yeah.
And a lot of people. Brad?
So Virga is a potential way that you can redistribute aerosols?
Yes.
Did you see any evidence when you had Virga? Did you see any enhanced aerosol in that vicinity?
So I'll say
Was it
that.
too hard to get it out of all the.
So I can't say that I've attempted that, but Ann Fridlin is working on that now, actually, and she's seen some evidence based on her Oracle's model study that's going on.
Was the HSRL on the P3 or was it on?
It was on the it was on the ER2 the first year, and then after that, for budget reasons, it was cut out of the experiment. So it was actually co-located with the 17 and 18 data sets on the P3. So yeah, that's why most of the data was from those 2 years. Larissa?
Is there a correlation between, it seems like, so I guess as you were just discussing in response to John's question, and the aerosols come from somewhere and they're correlated with some kind of synoptic scale environment. So is there some kind of correlation between estimated inversion strength and the amount of aerosol that you have? Did you look at that, or?
To be determined. I haven't yet looked totally at that. Just we wanted to see contact versus non-contact and see is there, a pathway, I guess.
And
to
are
say.
the EISs different for contact versus no contact?
Generally speaking, there's an even number, I guess. Well, there's a lot fewer, I guess, in this particular case. EIS data set or data with really high EIS, I guess, compared to low EIS. Most of the data was in low EIS environments, but in the contact, I guess, versus non-contact between the two. Again, and also too, I guess the amount that was in non-contact for high EIS was especially limited, but we still had, I think, it was roughly 2,500 profiles, I think, to analyze relative to about 20,000 or so for the
So
low
did
EIS.
you look at whether the distribution of EISs in contact versus no contact are different?
Can't say that definitively, but I will definitely take a look. So,
Okay, because that seems critical to the
It-
interpretation.
yeah, definitely will be. I agree with that. So, Terry.
What did you use for your attenuation flag when you did your agent for HSRL?
So there's a cloud mask screening, I guess, variable in there to, reason I guess I was able to get it done is because the data's already screened out and quality controlled, so it's okay, cloud, no cloud, and smoke versus no smoke, and that's where. Elizabeth.
Apologize if this comes out of left field. I haven't sat through a cloud aerosol talk in a while.
Mm-hmm.
Have there been any observational in situ studies that have proven the second this precipitation aerosol and direct effect? And if not, at what point do we start, if we keep not proving this hypothesis,
Yeah. So.
where do you go?
Other ones, they've looked at them, I think, but with very limited success, as far as I know, existing data sets from other literature. But that said, I think the whole premise of oracles was specifically, well, it was mostly for aerosol direct effects, but, they threw on, the radar, the RSP, a lot of other instruments too, and cloud approach, for specifically to tackle that, to give, collect a big enough data set to really, look at the, first and especially second indirect effects.
So you're arguing you're supporting the second indirect effect, right?
We will be,
So
yeah.
are you arguing that's the first time that this has been seen then?
In this context, I don't think so. Well, but, yeah, not entirely sure actually, but at least with, the second indirect effect, I guess there's more, work that's kind of ongoing right now. The Miami group, I think, is specifically tackling this one, the second indirect, or the second.
So
The
then
aerosol
your answer to Liz's question is then there's lots of work that has looked at the second indirect effect that supports it, or there's some work?
I think so. Well, yeah,
or
there's a lot
something
of
in between?
satellite, and I know Allison, she's done a lot of work on that. That's kind of shown that too, with her regression
I
analyses.
think there's a lot of satellite work in particular that has
Yeah.
shown evidence for it. It's
Mhm.
difficult, when you say prove, that's a
Mhm.
strong word.
Yeah.
I would say evidence for it, and I would say then the problem is field campaigns
Yeah.
have sometimes shown it, sometimes not, but
Mhm.
a lot of that may be due to this environmental coupling. So I think some of the questions have, and I think you've answered them well, but just to sort of put another point on that,
Mhm.
I think a lot of the discrepancy between field observations is because they've occurred in different environments, looking at different cloud regimes, and
Mhm.
that's what sort of needs to be sorted out, so.
Yep.
That's what Andrew's trying to do.
Still ongoing, yep. Anybody else?
Okay, let's thank Andrew one more time. So we'll take a short break, let everybody else leaves, and then if the committee could reconvene here in about 5 minutes' time, we'll start the post-defense questioning.
There's more cookies people